Hello everyone and welcome to Grantham Physics 220 Week 6 Laboratory video. So this week we're going to be using the interactive physics videos again. Specifically we're going to be using the ballistic pendulum file that you guys should have downloaded by now. So in the simulation object, the projectile strikes and becomes embedded in a block of wood suspended from the ceiling by two strings. The strings mass are negligible, so the block of wood and the bullet are important, the strings are not. We asked to read the measurement tables and make calculations concerning the total mechanical energy and momentum. Energy and momentum are conserved since friction and air resistance are absent. These measurements will result in the determination of the initial velocity of the projectile. Actually, the initial velocity and the velocity upon impact are identical, so once you find one, you know them both. And then fill in the blanks, and then we'll move on from there. So the first thing I'll do is go over to where the lab files are and open that up. So here are our files, and notice we're going to open the ballistic pendulum one. So I'm going to hit that. It's going to have the interactive physics open up, and then we can start to go through this. Okay, so here's our simulation here. Notice you have the mass of the bullet, and you have the mass of the block. Notice the mass of the bullet's given as 0.001 kilograms, or basically pretty close to 1 gram, and the mass of the block is 0.05 kilograms, and the value of gravity is set at 9.81 meters per second squared. So if I let this run through, notice it fires up, and it stops from there, and it goes back down. So again, we're going to have to run through this piece by piece. The really nice thing about this is you can literally just grab this. Once you get it going, you can grab this and move it over. So I'm going to reset this, and then kind of let it go, and stop, and then we can move this back and forth. So the key point of interest here is the ability to, you want to look at the heights involved before and after the collision. So before the collision, notice what the height is given as, because if you'll notice, one of the things we are concerned here is with the delta t. Okay, how did that hit? So what the change in the height was. So if we come back here, we notice where it starts at. We can let it play. Watch till right about where it goes up to where it stops. And what you can do here is you can play with the time. You get the maximum. It's actually it's starting to go back the smallest value on, since it's negative, that's going to be the maximum height. Notice it's about negative 0.79. So now you can find the change in y that you can then put in at this point. Now, from here we're going to have to use some of our physics to determine what's going on. Particularly, we want to know what the potential energy is at this situation right here. And it's total m times g times our little delta y here. Excuse me. Okay. So that's going to give us our energy we're looking for. Okay, so now at this point you should have the potential energy of the block. So what we're going to do here is we're going to use the relationship that all of the energy of the block and bullet together, the instant they hit, they had a certain kinetic energy that was then transferred into potential energy. So we're saying the kinetic energy of, I'll do little b, big B for block and bullet, equals potential energy that we've already got of the block and the bullet. Which means 1/2, excuse me, and it's m plus m v squared, where we're saying m plus m is the mass of the system, equals little m plus big M, where I'm saying little m is the bullet, big M is the block. Remember we talked about case in previous labs. G times our delta y. Okay. Whoops. Okay, don't worry about that part. So what that means, if we manipulate this, we get that the block and the bullet have a velocity equal to 2g times the potential energy. Okay? So now that we've determined that, we then use the conservation of momentum, which says remember momentum is mv, so P equals mv. So in this case, the P initial has to equal the P final. We're talking about the collision of the bullet with the block. So the mass of the bullet times the velocity of the bullet has to equal the total mass. Sorry for that, it doesn't autocorrect. Total mass times this capital V, which we just calculated there. So then you're going to get a relationship that the little v is the total mass over the smaller mass times v. Okay. Now in this situation, you can notice that obviously the total mass is going to be much bigger than the mass of just the bullet. If we come back over here, you notice it's about 5 times bigger. So you're going to get something that's equivalent to about 6 times that. So then you should be able to then realize that that factor of 6 times that smaller velocity is going to give you a much larger one for the bullet. Now another point I'd like to point out here, and this is where you can actually see this coming into play, is you notice it has v bullet calculated, which you would get here. Notice it also starts with a delta t. What it's asking you to do there is calculate the time it takes for the bullet to go from where it starts, notice the time 0, to where it collides with the block. Now, this is going to involve you ticking it back until the instant it hits it, which is kind of tricky. You have to really kind of step it back. To right about here, you notice the time is very short, and I can tick it through until maybe you can consider that the point of interaction. So it's 0.025 seconds. The other thing you notice is it gives you an X position. So at this point it's at 1.452. If we go all the way back to the beginning, it's you could calculate the distance of the collision there to determine an actual numerical value. Notice it doesn't. So this is the actual position of the block, and you have to determine roughly from where is this as this moves back and forth to how far the bullet actually moves before it collides it. But you still should get a decent idea of how far it goes before, and then thus you should be able to determine the value of the actual velocity and compare it to the number you calculated over here. And then that should give you your answer. Well, that's it for week 6. Again, I hope this will help you work with the labs. And if any questions, anytime you have any questions, please email your instructor.